let's see if we can get it. Let's see if we can get it to like step by step, you know. Maybe let's do step by step. So let's do step by step where this is going to be main alt 2. We're going to have main pi as a new one. And then we put it here, and then we'll just do, okay, so we'll just do this. Then we will do this is the initialization. Oh no, why test? Test, no. Main alt, that's the one that I was putting in here. Okay, so let's just add everything up here. And then we're gonna copy the symbolic, that's the symbolic stuff. No, that's the initialization. Okay, so Oracle init, then we've got the symbols, and then we have the the substitutions, the dictionary that comes in kind of here. So that's going to be the substitutions dictionary. That's just dictionary, right? So yeah, so this is just basically preparing the dictionary. And then we're going to have, and then we should do one by one, right? So then we should kind of like, I want to do like these. First step is we do, so the first thing we'll do is, so this is the symbolic, and then we're gonna have the numerical, small for a pass, and the numerical for a pass. Okay, so this is kind of what we're testing, right? This is what we're testing, and then and here we want to print both. So what we want to do is we want to test and essentially, I guess, print both, right? So the comparison is going to be well, we can already do here. So the Z1 sim, it equals these. Okay, it's gotten smarter. That's good, actually. That's cool. It understood what is it that I want to do. And the comparison, let's just do two printouts, right? So we print these. It's interesting. Cool. That's good prediction there, actually. Let's run this. I think it looks good. Now I basically, taking a look at the main pi, I want code to compare the ZSIM and ZSIM. I will just say like out sim and out NP, or let's do it like this. So we're gonna have here one out sim equals Z1 sim, and out NP equals Z1. And just what I'm doing is I'm just doing this so that I can generalize this stuff. And what are we doing? What have we done? No, okay. So this stuff here. Okay, perfect. Is my volume of the microphone good yet? Stop. Cool. Okay, just first of all, so that worked actually, right? Yeah, that works. Now I want to compare these. So, Mr. AI, please generate code to compare outsim and outnp as part of the code in MainPy. Let's see what it does. Outsim doesn't know. It's yeah, of course it's a symbolic expression, right? It's still substitution because it's a matrix to NumPy array. Okay, so it's telling me to lambdify this. Lambdify. And then use NumPy all close to compare both arrays. Strike off for that. Okay, so let's see. So that would be basically that would just be basically these. Then evaluate the function. Interesting. Okay, so we're turning that into a function. And then comparison result, exactly. And we have a tolerance. And then we print the actual comparison result. Let's see what happens if I run this. True. Okay. If I would do something like these, I cannot. I cannot add 5 in a symbolic expression. Can I? How do I add a symbol? SP symbols. But that's a symbol, right? That's not a. I cannot add a 5. That's weird. But I mean, let's say we add something here. It's very stupid, but false. Okay. I still would like to print these, and then print the out NP. And so here basically say print matrices, matrix. Okay. So we still get to see them, and now they're obviously not because of these 6 here. Okay, I should have done this. I should have done this from the beginning, because now we can see they're the same. I mean, you can't see because my face is on it. Maybe I'll just move my face around. Give me a second. Move the webcam, maybe. Ugh, how can I do that? Webcam. No. Why I can't move my webcam? When I select it, it actually selects me the screen. Whatever. Okay, but you get what I mean, right? They're here at the bottom of the page. Why I can't move my? You see now. I guess you yeah, you see they're the same. Okay, cool. I can actually do that. Probably like this better. Anyway, okay. So now we add like line by line. So this is the same. Now that's my guess is the problem might be in the loss function actually. Okay, so we do these. Well, that actually should just be essentially yeah, so we do these, and then we do, whoa, sorry guys, this actually goes here and this goes here, and the symbolic, we apply this function here, and by the way, this should just be, okay, whatever, A1. Okay, so let's see now. This just applies a function. Works the same, works good. Now we're gonna do the last part, which is this. So the W2 and stuff. That's good. Oops, what have I done? See. Okay, numerical pass, and so Z1 is going to be in here, and Z2 and P is going to be here. Okay. So let's see. Is that the same? True, that's the same. Good. That's good. It means essentially there's nothing too odd about these so far. Now is what we're getting. Now it's going to be interesting, right? If that actually is true, I'm going to be very happy, because I'm afraid it's either these or it's either how the loss function is described that is not working well. Could also be the derivative. Could also be the way that the derivative is done. But then it's like odd, right? Like, why would a derivative, the symbolic derivative, wouldn't give me the same result as like manually applying the chain rule? But okay, let's put the softmax. Okay, so we have the softmax function here. We're going to define the functions here at the top. Softmax functions. So we've got first the NP one, and then we've got the symbolic one. Okay, so we've got the functions in here to be called. Remember this one, actually they don't have the correction. I don't know, let's see. There was a difference, I think. In one case we're applying a correction with the exponential, I think. But let's see. And now essentially what we're doing is, so far so good. So if we now do the prediction on the symbolic pass, we do, no, that's the numerical one. Is that? No, that's the, okay, that's good. Softmax. You see, that's the funny thing, right? Because I think the funny bit here is that for some reason we're doing, like, that's not apply, like here you're applying a function to the expression, while here I'm running. Okay, there's also an apply func in here, right? But it does something a bit funkier. I'm almost sure that might be the problem, actually. But anyway, we do these ypred, and now ypred is here, and then on the numerical side we do this, and then that's the output that we're going to compare here. Wait a second, that is actually pretty stupid. True, okay, but that's true though. Okay, that's good. Very interesting. Okay. So that's very interesting. Then let's go with the last one, the cross entropy loss. The numerical calculation is this one. And the symbolic one is this one, duoid. loss is what you're substituting. What happened here? Terminated. True. Okay. Okay. That is a surprise. That is a surprise to me. Okay. So so the problem is in the in the derivative, right? The problem is in the differentiation. And that's where it gets tricky, right? Because how do we even check that? Okay, so I'm so what now, right? I mean, okay, so you've got basically here we're just, this is what we're saying, right? So we're saying gradient of the loss, and that's what we're saying, that this is it. Whereas now we do the derivative, so we basically now we do the numerical differentiation, where we just say, interesting, right? It's like half baked in there, but it's actually getting there. I'm curious, where is it taking it from? Is it really reading it from the other file, or is it really trying to do the actual differentiation? Because this is what, again, the gradient. Okay, wait a second. That's the gradient. So maybe the first thing is that's. Maybe we were comparing apples with how you say that, pears. Wait. Because that's the gradient. Let's bring that down, maybe. And now let's do the div thing. Because really, what we should be doing is this numerical div, that is basically the symbolic div. So let's not with respect to W2, but like with respect to Y pred. Also not. With respect of Z2. Right? That's right. First I should do the rest with respect to Z2. Because that's basically or with respect to that outcome. Let's first try these. So this is basically, because it's dz2, right? Like that's how I named it in here. So symbolic loss function. I mean, here I'm just thinking it might be faster if I do the substitution before. But let's see. I don't know if that is going to be fast enough though. This will easily, whoa. Well, it says value. I can't calculate the derivative with respect to these, because that is a huge fucking expression. Really. Really. And if I do this, but I can do this with respect to W2. This I don't get it. Is it because? Yeah, probably. Because that's kind of what makes sense, right? Because that's the actual variable, I would say. This is just a calculation, Z2, although that is, because when we're doing it from a like directly with a differentiation with the diff, with the gradient, is like where you're really looking at the actual variables, right? Does that make sense? I guess maybe if the loss was defined a little differently, if the loss was defined symbolically with the Z2 symbols and stuff, maybe. You know, I mean, it's not working in the previous cases because essentially ypred or Z2 are like expressions themselves, right? So they're not the symbols, and so you can't really do a derivative on that. I think we need to let this run for a few minutes, but I think that's the yeah. But I'm sure that's now definitely not going to work. Well. First of all, it's not going to work because obviously I do need to do something else on the numerical side, which is I do need to do this, because that's the point, right? We just use that here because we need that term. Sim and sim. Oh, whoa. Okay. And I'll let this run, and then let's go read a bit about AutoGrad. Okay. So PyTorch AutoGrad tutorial. Okay, so let's go through a simple example. So, okay, or let's go through the theory maybe, right? So AutoGrad features a part of what make parts flexible and fast building machine learning projects. So allows for rapid and easy computation of multiple partial derivatives as gradients over complex computations. It traces your computation dynamically at runtime, meaning that if your model has decision branches, it loops those lengths are not known until runtime. Okay. Create gradients to drive learning. This combined with the fact that your models are built in Python, flexibility. The machine learning model is a function with inputs and outputs, and we'll treat it as I-dimensional vector. So the model is like this, and then essentially our output of interest will be the model's loss. The loss function is a single value scalar function with model's output. This function is how far off your model is prediction. We know all these. After this point, we'll often omit the vector signs. Whenever entering a model, we want to minimize the loss. In the last case, the perfect model is adjusting the learning weights. Adjust the parameters in the function such that the loss is 0 for all inputs. In the real world, it means an iterative process of nudging learning weights. How do we decide how far in which direction to nudge the weights? Okay, so which means making its first derivative with respect to the input equal to 0. Recall though that the loss is not directly derived from the input, but a function of the model's output, which is a function of the input directly. So derivative of the loss by by the chain rule of differentiation calculus, we have, okay, so that's the chain rule thing, right? So it's basically what we're saying is that the derivative of this is basically the derivative of the loss function with respect to y, and the derivative of y with respect to x. Is where things get complex. The partial derivative of the model outputs with respect to its inputs, if we were to expand the expansion using the chain rule again, would involve many local partial derivatives over every multiplied learning weight, every activation function, and every other mathematical transformation in the model. The full expression for each such partial derivative is the sum of the products of the local gradients of every possible path through the computation graph and the variable whose gradient I'm trying to measure. In particular, the gradients over the learning weights are introduced. Each weight to loss function to 0. Exactly. Since the number of such local derivatives will tend to go exponentially, terms as autograph comes in. So essentially, what they're saying is, you could make like a whole, you could make like the whole derivative as a one-time kind of thing, but then it would become very complex. It tracks the history. So the whole thing with AutoGrad is basically tracks the history of every computation. Every computed tensor in the PyTorch model carries a history of its inputs, tensors, and function used to grade it, combined with the fact that PyTorch functions tensors have a built-in implementation for computing their own derivatives. Okay. So the PyTorch functions meant to act on tensors have a built-in implementation for computing their own derivatives. This greatly speeds the computation of the local derivatives needed for learning. Simple example. Okay, some imports. An input tensor full of evenly spaced values on an interval 0 to 2 pi, and specify requires grad equals true, like most functions that create tensors, torch in space except options. Okay, so what this does is it creates a tensor. Okay, it will transfer the computation with you apply the sinus function. Next, we'll perform a computation. So you have the computation now on these. Okay. Okay, so this is the sinus of each of the elements of the tensor. We'll print it. Let's have a look at the tensor B. When we print it, we see indicated that when we print B, we see an indicator that is tracking its computation history. Seen backwards. Okay, interesting. Yeah. This grad fn is a gradient function. Probably it gives us the hint that when we execute the backpropagation step, the gradients will need to compute the derivatives of sinus for all its tensor inputs. I mean, essentially, AutoGrad is just the So essentially, AutoGrad is just the chain rule, right? Let's go back to this because I have to. Okay, it hasn't finished yet, guys. I have to stop the video now. I'll post an update later. Bye bye.